Hello everyone, welcome to Probability and Statistics for Data Science. In this video I'm going to give an overview of principal component analysis and low rank models. These are techniques that are used to analyze data where each data point consists of a large number of features, so that we need to apply some kind of dimensionality reduction in order to make sense of the data. In the case of low rank models, the data are usually arranged as matrices, and the most famous application for these low rank models is performing collaborative filtering in recommender systems, where you want to aggregate data from many users and many products to try to estimate the preferences of users that have not yet tried a product. But let's get to it. And I forgot to warn you that this is an overview. So I'm going to be just stating some stuff that I'm not going to delve deep into because otherwise the video would take 3 hours, but you can find all the details in the individual videos or in the book. Okay, so let's get to it. Our motivation is to model data that has multiple features. So this could be just, like a normal problem where you have like different features, for example, describing patients in a hospital, like their blood pressure, their age, etc. Or it could be things like images, where we could interpret each pixel as a feature, and I show you images here because we're going to see some examples. Or it could also be matrix valued data, where each data point is associated with two entities. For example, here, this is the rating that Bob gave to the movie The Dark Knight. Our plan is going to be to explain the covariance matrix and how it pertains to the problem of modeling data points that consist of multiple features. Then we're going to talk about principal component analysis, which builds upon covariance matrices to achieve a dimensionality reduction, which is what we're going to talk about right after. Then we're going to cover low rank models that enable us to analyze matrix valued data like the one I had just shown you. And finally, we're going to explain how to use these low rank models to perform matrix completion, which is very important for collaborative filtering in recommender systems. We have a lot to cover, so let's go. Our goal is to describe data with multiple features. A very useful way to model data with multiple features, which is uncertain, is to model each entry, each feature as a random variable, and then group all of the random variables into a random vector, which in this case has d entries because we have d features. And now what we're going to worry about is how can we understand the structure of a random vector that has so many features. It's not completely obvious. A first step is to take the entry-wise mean of each of the features, and if you put that into a vector, that gives you the mean of the whole vector, and that's you can interpret it as the average data point. Let's visualize what we're talking about. In this case, we have a Gaussian random vector that has this joint density. The mean, because this is a Gaussian random vector, happens to be in the middle. And remember that in the case of Gaussian random vectors, the mean is actually a parameter of this parametric model, but that's not important here. Okay, the point is that the mean gives you some kind of summary of this high dimensional vector. In this case, the vector only has two entries, 1 and 2, so that we can actually visualize the joint density. When you have data, as opposed to a random vector, if you want to approximate the mean of the random vector that could have generated this data, a reasonable way to do it is to take the sample mean of the whole vector, which is the sample mean of the individual entries. Here we have a data point, again, with two features that we can visualize things easily, which are basically, the features are the latitude and longitude of cities in Canada. And if we visualize the sample mean, basically that is obtained by averaging the latitude, averaging the longitude, and that gives us an average data point, which is in the middle of Canada, more or less. The real interest in applying, in kind of analyzing this higher dimensional data, maybe not the real interest, but the real challenges arise when there are many, many features. So in order to illustrate that, here we're going to consider images from several subjects, each of which has 4096 pixels. So we no longer have just two features, we have 4096 features. Here you can also compute this sample mean, which means the sample mean of each pixel, and visualize it. And that gives you a sample mean, which is an average phase in this dataset. Of course, just working with averages doesn't get you very far. It's a nice summary of the dataset, but it doesn't convey that much information. And because of that, we would like some way of summarizing additional information captured in the dataset that is common across different data points. And a concept that is very important to be able to achieve that is the variance. Okay, for a single random variable, the variance tells us the average variation, the squared average variation of the random variable around its mean. That is not enough for a random vector, right? You could do the variation of each of the entries around the mean, but then you would not capture the relationship between the entries. So instead, what we can do for random vectors is we can look at the variance of linear combinations of the entries, and this is very powerful. We'll see in a moment how. It turns out why it's very powerful. It turns out that all of these variances of linear combinations of any of the entries of the vector are captured by the covariance matrix of the random vector. The first time you see the covariance matrix, it seems that you're just stacking variances and covariances. So the covariance matrix is the variance of the entries in the diagonal, and then it has the covariance of every pair of entries in the off diagonal. But this is not why the covariance matrix of a random vector is useful. It's useful because the covariance matrix of a random vector immediately gives you the variance of any linear combination of the entries of the random vector. So here A is a vector with the entries that is completely arbitrary. You can put in whatever you want. If you're wondering about the mean of that linear combination of the entries of X, you can obtain it easily by applying A transpose to the left of the covariance matrix and A to the right, and boom, you have that variance. You don't need access to the original random vector itself. All of this information is contained within the covariance matrix. Why is that important? Because then you can actually find out in what directions there is more variance, and those are the directions that usually capture the most information. In order to visualize that, we're going to focus on this random vector. And again, we do a lot of examples with just two features, just because they're much easier to visualize and understand what's going on. But the real interest here is in doing this when there are many more features. Okay, so this random vector has that mean, and it has this covariance matrix. If you want to some more information about what the covariance matrix actually means for the shape of the joint PDF in Gaussian random vectors, there's a video about that. I encourage you to take a look. Okay, so now we're trying to characterize where this random vector has the most variance, because often when you see more variance in a data set, that's where there's more information. If we just picked a direction at random here, okay, characterized by this unit norm vector, a way we could characterize the variance is just by taking the inner product of this vector with the random vector and computing the variance. But as I have just told you, you can actually compute that directly from the covariance matrix, okay? So this variance of any inner product between A and X is actually given by A transpose covariance matrix times A. So now I can consider all possible values of A here in this unit circle, and this function that I have plotted here, which is this function, gives you the value of the variance in every possible direction. Why do I focus on the unit circle? Because those are unit norm vectors. When I take the inner product with a unit norm vector, that tells me the variance in that direction, okay? And I can plot the variances in the different directions for this random vector, and what I see is that, this is the value for B, but there are higher and lower values. And if I want more information, like the directions that capture the most information, I'm going to want to find these guys. How can I find those guys? Well, I can find those guys by performing the eigen-decomposition of the covariance matrix, and that's going to identify the directions of maximum variance. This is not obvious. It's based on the spectral theorem, and we have a video just about that, so I encourage you to take a look. But that's how you can identify them. The components of the data, or of the random vector, sorry, in that direction are called the principal components. So essentially, if you perform the eigen-decomposition of the covariance matrix of this vector, you're going to be able to find this vector, which is basically the one that maximizes this function that we have plotted before. Again, you find it by performing the eigen-decomposition and looking at the largest eigenvalue in that eigen-decomposition. If you project, this now is the joint PDF of X, okay? If you project X onto this line, you obtain a random variable that has maximal variance, okay? Between the random variables that you would obtain by projecting on any other direction. That one is going to have the largest variance, and the result of that projection gives you the first principal component. It just so happens that here we just have two features. If we had more features, the second principal component would give you the direction orthogonal to the first principal direction that has the most variance, and so on and so forth. Here we just have two. The last one gives you the least variant. Okay, so this is the other eigenvector of the covariance matrix. And in that direction, which is this one, we observe the least variance. So if we project the joint PDF of X onto that direction, we get a random variable that has the least variance. Okay, so in this case, if we wanted to reduce dimensionality, we should just preserve the first principal component, and that would preserve the most variance if we want a single random variable that approximates this random vector. So this is the original joint PDF. You can think of computing the principal components as rotating this PDF, so that we have maximal variance in this direction and minimum variance in this direction. We can do something very similar when we have a data set of d-dimensional data points. We interpret them as samples from a random vector, and we compute a sample covariance matrix that has variances in the diagonal and covariances in the off-diagonal. Exactly like in the case of the covariance matrix, the first time you see this, you're like, oh, here we're just kind of keeping track of all the variances and the covariances. But the sample covariance matrix is actually much more powerful. It actually gives you the inner product between, the sample variance of the inner product of any linear combination of the entries of the data. Let me illustrate this with the cities in Canada. These cities in Canada have this sample covariance matrix. How do we compute it? By computing the sample variance of the longitude, sample variance of the latitude, and the covariance between them, the sample covariance between them. And actually, that sample covariance matrix is going to give us the sample variance of any linear combination of the data points. So see that the linear combination has to be the same for each data point. So for example, we sum all the data points, or we sum all the data points except the last one and we subtract the last one. Whatever linear combination you can imagine. If you want the sample variance of that linear combination, you can obtain it by just taking the coefficients of the linear combination, multiplying them by the sample covariance matrix, and then multiplying them again by the coefficients. So the sample covariance matrix actually has a lot of information about the structure of this data set. Again, we're going to wonder what are the directions of this multidimensional data set that have the most variance. How would we find the variance in the direction of B, the sample variance? Well, we take the inner product of a unit norm vector in this direction times the centered data, and it turns out that this is given by this function that I'm plotting here. And we're going to again restrict ourselves to the unit norm circle because we're interested in the variance in the sample variance in a certain direction. So we want a unit norm vector. If I just scale this vector, of course, I'm going to see more sample variance just because I'm scaling the coefficient, right? So again, what do we observe? This is the sample variance for that particular direction. There is a maximum here. again, by the spectral theorem, the maximum can be found by performing principal component analysis, which is basically performing the eigendecomposition of the sample covariance matrix, which gives you the directions of maximum sample variance in this case. The components in those directions are called the principal components of the data set. Here, the first eigenvector, by first eigenvector I mean the one associated with the largest eigenvalue, is this direction over here, where this function that we had plotted is maximized on the unit circle, and that's the direction. When we project the data onto that direction, we're going to see maximum sample variance. Okay, so these are the individual projections in this rock plot of each of the data points onto that direction. We see maximum variance. That means that it's a more informative direction. If we looked at, again, here we only have two features. So the second eigenvector is going to be the one with the least sample variance. It's that direction over there. It's a direction of minimum sample variance on the data. If you look at the projections onto that direction, you see very little spread. Okay, that direction is not giving us a lot of information in this data set. Okay, just as in the case of the random vector, you can think of computing the principal components as rotating. Here, unfortunately, Canada didn't help me very much here because, you know, like it's almost aligned, but it aligns it a little bit more. Okay, like this, the trend is a little bit going down here. You can see that the principal components rotated slightly, so we do have maximum variance in this direction, minimum variance in this direction. The whole point of computing the principal components is to actually, an important use for principal component analysis is dealing with data that have a large number of features, which can be very difficult to analyze or process. And we want to do dimensionality reduction while preserving as much information as possible. And we can do this by applying principal component analysis. And this is commonly done as a pre-processing step in many applications, even if you're going to do like some sophisticated stuff afterwards. It turns out that the first K principal directions span the subspace that capture the most variance in the data. Here we're going to see an example with some wheat seeds. So here our data corresponds to seeds from different varieties of wheat. And there's 7 features. So this is a 7-dimensional vector, and we want to visualize it. In order to visualize it, we want to have to be able to kind of project it onto 2 dimensions. We want to capture as much variance as possible in the data. We choose the 2 first principal components. I do this often, where I tell you an answer and then I put the question. I'm sorry about that. So how could you visualize the data in 2 dimensions? Maybe, like pause a moment and see if you agree with what I just said. Basically, what we're going to do is we take the 2 first principal components because they capture the most variance in the data. And here we see that they actually preserve the structure in the sense that we could then, for example, cluster the different wheat seeds in this low dimensional space, and it would be a pretty reasonable clustering. So we have managed to preserve the structure in the data with just 2 dimensions, while the original data points were in 7 dimensions. What happens when we have 4096 dimensions, which is the case of this phase dataset? Well, we can do the same. Let's take a look at what the principal directions look like, the ones that capture the most data for this dataset. They look like that. So the directions that capture the most data have, like features of faces like eyes, noses, mouths, mustaches. The eyebrows are very important, and also illumination issues. Like, for example, here captures illumination on the left. The second principal direction captures illumination on the left. So these are the factors that capture the most variance in this dataset. As we look at the principal directions associated with smaller and smaller eigenvalues, they capture finer features in the data that don't have as much variance, and in the end, they're almost noise. It's important to highlight that for certain tasks, these finer features might actually be important, and in that case you have to be a bit careful with just maximizing the variance. Okay, so this is a limitation of this technique, but the truth is that it allows you to find low-dimensional representations that are pretty good with a very small number of parameters. So what do I mean by that? Well, now that we have these principal directions, we can look at the coefficients corresponding to each of the faces. So in this case, this face over here, and we can obtain a low-dimensional approximation by looking at the principal component corresponding to that face and weighting it by the corresponding principal direction. So here in blue, I have 5 numbers that could be used to represent that face. We can visualize what the information those 5 numbers capture by multiplying each of them by the corresponding principal direction and reconstructing the phase approximation. And it's not amazing, but it's only 5 numbers. So it's actually not that bad. Sorry for that awkward arrow. So this is the approximation corresponding to only those 5 numbers. And now we could do, we could use those 5 numbers for different things, like maybe clustering the different faces, doing classification, so on, with a very small number, in very low dimensionality, with a very small number of components. Let's just visualize this approximation for different dimensionalities of the approximation. This is the original phase, k equals 5, k equals 10. At 10, we can already capture glasses, kind of. At 20, we can capture mustaches. These are only 20 numbers. It's not so bad. At 30, we get much more details. 50. At 100, you already capture the fact that he's moving to the side. And 300 is the full dimensionality in this case because we only have 300 people. Okay. Because, just to be clear what I'm saying here, like each of these principal directions has 4096 pixels. I hope that was clear. Okay, so now we're going to shift to matrix valued data, and we're going to use similar ideas to model this type of data, where again we have matrix valued data where each data point is associated to two entities, with two entities. In this case, Bob, who has watched The Dark Knight and decided they didn't like it, so they gave it a 1 out of 5. A way to model this kind of data is by first centering the data. That's not very important. We always center. And then saying, okay, you know what? I can express the ratings of each user by using a fixed pattern of ratings and just scaling it by a fixed number. Okay. The idea is that different people might similar people might like similar things. In this case, Bob and Molly are similar and they like romantic movies and they don't like superhero movies. Okay, and Mary and Larry are the opposite way. In general, it's going to be difficult to find a single factor that explains the ratings for all the users and the products, but maybe you can find a small number of factors that allow you to approximate the data well. Notice that here, the original matrix has, there's 6 movies and 4 users, so there's like 24 data points, and our model here has the mean plus 6 coefficients for the movies, plus 4 coefficients for the user, so only 11 parameters. In matrices that are much larger, you can reduce the number of parameters much more dramatically using this kind of models. Okay, so the idea of a low-rank model is exactly the same as I just explained, except that instead of having a single pattern for the movies and a single pattern for the users, you have several patterns, R for the movies and several patterns for the users, so that correspond. And then you multiply for a certain movie and a certain user, you take the coefficient corresponding to each of the factors, you multiply by the corresponding coefficient, so user coefficient, you multiply it by the movie coefficient, and you add them all together, and that gives you your estimate of the rating. In our matrix completion video, we used a rank 3 model, so there would be 3 of these guys. And then we would add the mean rating of the movie. Here I'm just assuming that this is already somehow centered. We can interpret this low rank model as performing dimensionality reduction of the rows or of the columns, because realize that now the rows in this approximation are all linear combinations of these R rows on the matrix on the right. So we have performed dimensionality reduction of each of the rows of this matrix. But at the same time, the columns of this matrix are now going to be approximated as linear combinations of these R vectors here. So we have performed dimensionality reduction of the columns of the matrix also at the same time. So this rank R approximation, here the rank is R because the approximation basically, because of what I just said, right? Like the approximation, if you do the product of these two matrices, you're going to have a matrix where all the columns are linear combinations of these guys and all the rows are linear combinations of those guys. So the rank of the matrix is R because that's the number of linearly independent columns and rows. It turns out, I kind of lost my thread there, but I was saying that this was like dimensionality reduction of the rows and dimensionality reduction of the columns. And the way to see this is by introducing the singular value decomposition, which is a decomposition that every matrix has, where we have these left singular vectors that span the columns, these right singular vectors that span the rows, and this diagonal matrix that weights each of these guys and these guys. This diagonal matrix has singular values that are non-negative. The left singular vectors are orthonormal and the right singular vectors are also orthonormal. So you can think of it as a basis for the column space, a basis for the row space, and one vector of each of these bases is combined by multiplying by the singular value. Because when you do this product, essentially what you're going to be doing is you take this column, multiplying it by the first singular value, and then multiply it by the transpose of that vector. So the first singular vector transpose, and then you're going to sum that to the second column times the second singular value times the second right singular vector. This is maybe not completely obvious, but you can review your linear algebra and you'll see that that is the case, that the singular value decomposition actually gives you a decomposition in terms of a sum of this matrix that you obtain when you multiply UL and VL transpose by the corresponding singular value. And the important thing here is that this gives you a matrix that has the same dimensions as the original matrix but has rank 1. And now you can interpret each of those components as rank 1 matrices, as I just said, that are orthogonal. So this is orthogonal in a certain inner product of matrices, and it has unit norms. So basically the contribution of that factor to the approximation here is completely dominated by the singular value, determined by the singular value. In fact, if you take the square of the singular values and you add them up, that gives you the norm of this whole matrix. So in a way, we have managed to decompose the whole matrix into different components that are all orthogonal to each other, and where the singular value tells you how much energy they bring to the whole matrix. Okay, their contribution to the whole matrix. So if you want to obtain a rank R approximation, it's just very natural to truncate and just say I'm going to keep the R components that correspond to the R largest singular values, and that's called the truncated SVD, and it's exactly equivalent to performing principal component analysis of the columns and the rows and performing dimensionality reduction by preserving only the R direction that capture the most variance. This is true up to centering, because when you do principal component analysis of the columns, you center the columns. When you do principal analysis of the rows, you center the rows, and whichever you want to do will depend on the application. But beyond that, apart from that, this is completely equivalent to just truncating the SVD, and this gives you the optimal approximation. This is just a norm that captures basically the squared error of all the entries, it gives you an optimal rank R approximation to the original matrix. These are the movie ratings. This rank 1 model that I originally showed you is obtained exactly by truncating the SVD and just preserving the largest singular value. Okay, and this is how we obtain. This is the left singular vector, and here I have multiplied the first singular value by the right singular value, right singular vector, the first right singular vector. And this gives you a reasonable approximation of the original matrix. What if some entries of the matrix are missing? And this is by far the more interesting application in recommender systems, because of course you're not going to be able to observe the ratings of all the users for all the products, and you want to estimate the ones that are missing. Here, for example, we don't know that Bob actually didn't like The Dark Knight because in this scenario, he hasn't seen the movie yet. So how can you exploit low rank models to solve this matrix completion problem where you want to estimate the missing entries? Because you could, in principle, insert any value. So this seems, a very difficult problem to solve. Well, if you make the assumption that there is low rank structure that you can exploit, the key is to realize that if you have enough observed data here, you can use that observed data to estimate the components of the low rank model, and then you multiply them together, boom, to obtain a matrix from which you can find out the missing entries. Okay, let's see how this works in practice. So in practice, we cannot expect the data to be exactly low rank. So what we do is we find the low rank matrix that is closest to the data by trying to minimize the approximation of this low rank model to the observed data. This is a non-convex cost function that is difficult to optimize. There are several methods to fit these kind of models. A simple one that we delve into deeper in the video on matrix completion is using the truncated SVD. So the truncated SVD is optimal. It achieves an optimal rank R approximation if you observe all the entries. But if you don't, that's no longer true. However, what you can do is you can do some naive imputation of the missing entries, for example, using the mean rating. Then you can compute a rank 1 approximation using the truncated SVD, and that gives you a better estimate of the missing entries that you can then re-impute to then further improve the low rank model. And that's how that's what we did in this case. Here the mean observed rating that we started by imputing is equal to 2.94, and here I'm showing you how the different estimates change along the iterations of alternating between imputing and computing the low rank model. And what we see is that first the estimates start closer to the naive imputation, and then they improve as we alternate between truncating the SVD, in this case to obtain a rank 1 approximation, but you could do this for any rank that you determine beforehand, and re-imputing. Okay, and our final estimate is pretty good. There are more details about this in the matrix completion video. Okay, so what have we learned? We have learned about the covariance matrix and how it captures the variance of any linear combination of a random vector or of a data set. We have talked about principal component analysis that allows us to identify the directions of maximum variance in a random vector or in a data set. We explained dimensionality reduction, where basically you exploit principal component analysis to obtain an optimal low dimensional representation of your data. Optimal if you restrict yourself to linear dimensionality reduction schemes. Then we moved on to low rank models, where you try to model matrix value data, and we saw that low rank models are very connected to principal component analysis, in the sense that if you use the truncated SVD to estimate the low rank model, essentially what you're doing is you're performing PCA on the columns and rows of the matrix at the same time. And then we explained how to exploit these low rank models to perform collaborative filtering. I don't know if I even said that this is called collaborative filtering, but basically estimating missing entries in this matrix value data, which is very useful, for example, for recommender systems. And that's all I got. Thank you very much.